Yeah, so my name is Andrea Bryant. I'm a PhD student at University of Chicago, and today I will talk about investigating the use of long-period seismology to explore Titan's interior. I'm aware that I'm actually quite new to seismology myself. I only began a couple years ago, so I will try to do a little bit of background for everyone. All right, so starting with Cassini, we learned a lot about the Saturnian system, but especially for this study, we learned a lot about Titan. And so there's actually a probe, the Huygens probe, that landed on the surface of Titan. And you can, if you go on YouTube, you can Google it or you can YouTube it and see the landing. It's landing through the haze, and you see some water ice pebbles on the surface. There's so much I could say about Titan, but for the sake of time, I'll just say it's an amazing natural astrobiology laboratory. I'm very excited to do some theory about it. Okay, so here is what we currently know about Titan. And so we know that there is a liquid water ocean underneath a very thick shell of ice that's between 50 and 150 kilometers deep. We don't know the exact compositions of this ice shell or the ocean, but we do know that there's water there. And also there could be some high pressure ice underneath the ocean. And this actually has very big astrobiological implications because it could actually act, if there is high pressure ice, it could act as a barrier from the enrichment of the ocean for potential life if it's there. And so yeah, so that's something that seismology can help us to constrain whether or not that's there. Okay, so this brings me to NASA Dragonfly. And so Dragonfly is a rotorcraft that will launch in 2027. And it'll take about 6 years or so to get to Titan. But this instrument will be loaded with many, many different instrument packages that are really, there's a very large focus for astrobio. And in particular, the seismometer, which is going to be on the other underside. You can see here it's like dangling, or it's up under the rotorcraft, but it's going to be tethered. It's tethered, and so it'll be lowered down at each location on Titan that's going to visit. And then measure the seismic activity there. And there also are these geophones, which are essentially less sensitive seismometers, and they're a bit smaller. They're going to be, there's two on the underside of the skids. And so, in particular, the seismometer, the geophones, and other instruments within this DragMet package are going to be looking to measure habitability. Okay. So Dragonfly seismology, in a nutshell, will help us to constrain the interior structure of Titan more precisely. And so seismology, similarly like on Earth, has helped us to understand more about the actual interior of Earth to like very great detail. And so we hope to be able to do a bit of the same on Titan. And so some possible causes of Titan quakes will be tidal flexing or cryovolcanoes, and then also like ice cracking events of various kinds. And then this is, of course, not a non-exhaustive list. And so we'll be able to put like very precise, more precise, hopefully, measurements on what's actually going on there. Okay, so now this brings me to the namesake of this talk, long period seismology. I'm talking about, so if you're familiar with seismograms, we have the body waves, so those are the P waves, compressive waves, and the shear waves, S waves. And then we have, later on, we have these surface waves. And so I'm looking, as opposed to using body waves, investigating, and particularly with these, I'm looking at methane clathrate models. What if I were to use the surface wave information, and particularly dispersion information, to be able to try to learn about Titan and maybe about the ice shell thickness. So let's see what I found. Okay, so starting with methane clathrates, for those of you who don't know what that is, so a clathrate is essentially, I like to say a water cage. And so you can see, I don't know if you can see this. This is essentially a structure of water molecules around, and they're entrapping a single molecule. And in the case of, or in the study, the molecule we're looking at would be methane. Okay, so imagine there's this molecule, and now we have tens of kilometers of these methane clathrates, and we think that this could be very possible and very plausible for the Titan conditions. And I think I forgot to mention, Titan surface is 94 Kelvin. So on the surface, methane, we have a hydrological cycle, but it's a methane hydrological cycle. 6% or 5 or 6% of the atmosphere is methane. And so we have, instead of lakes of water, lakes of hydrocarbons and lakes of methane. When we have this liquid methane and ice under Titan temperatures and pressures, they will readily form these methane clathrates, and this has been shown in the laboratory. So it's thought that there most likely will be lots of these methane clathrates on Titan. And so the models that we considered were essentially, they were all the same. So we were looking at 100-kilometer thick ice shell and just varying the clathrate lid thickness. So the clathrates were just at the surface, so hence the clathrate lid. These are all spherically symmetric models. They were generated with an open source code called Planet Profile. If you're interested in generating this, it's on GitHub. Also, I can show you how to get it, or you can just Google it. And there's a ton of other bodies you can look at there as well. And so we simulated a magnitude 3 quake, and then these were the data that we'll be looking at come from a 3-kilometer source depth, so 3 kilometers deep within the ice. Okay, so from this study, this was led by Angela Maruziak, who is now a professor at the University of Arizona. And so we actually saw some small differences in dispersion between two of the models in particular that we were looking at in that paper. So that was the 10-kilometer clathrate lid and the pure water ice shell. And so just as a primer about dispersion, it's related to the material properties of the ice shell, and particularly in the case of elastic waves that we're looking at here. And so this wave speed depends on frequency, and that's kind of like the meat of what dispersion is seeing how this wave speed or the group velocities, they change as a function of frequency. And so we saw like about 2% difference, a 2% difference between the dispersion. So that's looking at this group velocity curve here. It's very small differences, but they're small enough that if you have a really high precision seismometer, you could actually detect that, which is actually, I found that quite intriguing. So I was like, well, let's dig deeper and see what else we can find. So this brings me to the setup of the project, of this long period study that I'm leading now. So I take theoretical dispersion curves. So it's all theoretical, but these are extra theoretical. And I can explain what that means later, or if you ask. So theoretical dispersion curves, they're generated with a code called Minios, and I'll elaborate on that. And then take these other AxiSim and Sysais, that's another code. So the different methods of doing these things. Seismograms to create these mock observational data, of which I would go and pick and calculate by hand and with a computer the group velocities for each Titan input model. And I'll show that across a range of distances and frequencies. So now I'll talk about the theoretical group velocities. And so these are looking at group velocity as a function of frequency, so group velocity on the y-axis and frequency on the x-axis, and I'm looking at different modes. So I'll talk about what these group velocities and phase velocities are, or group velocities are, and then what the modes are. So group velocity, if you look on the right-hand side, it's the actual velocity of the wave packet that's encapsulating the bigger, larger scale structure of our seismograms. And the phase velocities, that's another measure of dispersion. It is the actual velocity of the peaks. And so when you have the group velocity not equal to the phase velocity, you know you have a dispersive wave. And so the tonal information, so modes, so if you remember from physics, the wave on a string analogy, or it's not an analogy, but it's the wave on a string representation of modes. The fundamental modes would be here. There's no node. First overtone, one node, second, third, second, and 2 and 3 nodes accordingly or respectively. And then you can go all the way up to, as many nodes and modes as you'd like to. So for this study, we actually looked at up to 3,000 overtones to create an entire seismogram. But here, we know that most of the information of this surface wave that we were looking at, and I forgot to mention that, it's a Rayleigh wave, it would normally be in the fundamental mode. But there's a surprise that I'll show you in the next slide. And so essentially what we found was that when we're comparing, when we're looking at the data, and I went and used actually this other data set and took the seismograms themselves and calculated the group velocities as opposed to just them being spit out from a code for me. Consistently, that the dispersion profiles, when we look at the different interior structures, they do like differ slightly, but then when we lay them on top of each other, essentially like there's very little differences, and it's so small that we probably would not, and not probably wouldn't, they would be smaller than what we could observe on Titan. And then also these Rayleigh waves, we thought that the information would be in the fundamental mode, but actually it was in the first overtone, which is a little interesting, and it's consistently so that case. So there's this yellow line is the first overtone, and so this blue little cloud thing is the 1 sigma standard deviation from these group velocity measurements, which are taken over a range of distances and frequencies. And so, yeah, it's a pretty strong thing that's happening, or signal that we're seeing for it not being in the fundamental mode. And so then that just shows that this method, we wouldn't be able to use body waves to, the surface wave, this particular surface wave as to diagnose the thickness of Titan's ice shell. So that's intriguing. And so I will dig deeper and see more about that in the future. All right, so a quick summary. I use data-driven models of Titan's interiors to compute Titan synthetic seismograms for comparison to real data that we'll get from Dragonfly in the mid-2030s. And in the study, we investigate energy trapped in the ice shell to determine the structure of Titan and the presence of surface clathrates, and aka long-period seismology. And while the surface waves observation that we saw in the study do not clearly determine ice shell thickness, we can constrain it using body wave arrivals, so PNS waves. And if you're interested in learning more about icy ocean seismology, and in particularly about some of the methodology that we were implementing, talk to me, or also consult Simon Stahler's paper. We're looking also at other icy ocean worlds as well. And then understanding the composition of Titan's interior, especially the ice shell and ocean, will have important implications for astrobiology and habitability studies. So thank you so much.
Hi, nice talk. So presumably, like in the lab, we don't have like kilometers of clathrates. So what does it take to extrapolate from just this lab-made amount to how it'll behave when it's this much as a medium?
Yeah, so we used this paper by Kalasova and Sotan. I think it's in like 2020. But that was, their paper is where we got the actual thermal models to model to model this for the clathrates. Yeah.
Thank you for the talk. I have a question that may be outside of the scope of what you do, but I know that the ice shell thickness can be a proxy for heat loss, and that can also kind of provide clues as to whether the ocean may be like a transient feature, or a more long-lived feature. Is that anything you can determine using the data that may be collected by Dragonfly or anything like that, or is that outside of the scope of? Because I mean, the longevity of the ocean, like if there is like a liquid water ocean beneath the ice layers, that could have implications in the habitability, whether it's like persisted over geologic timescales.
Yeah, I mean, we can constrain with seismology, the composition and the depth, but regarding, yeah, it's a little bit outside of my purview.
Okay, I apologize.
No, it's okay, yeah. Good question, though, thank you.
So I'm curious, what is the amount of confidence we have that there's a high pressure ice layer on the bottom instead of, a direct contact with the ocean?
Yeah, I mean, we don't have like any confidence to say. I mean, we think that there could be. I think there's definitely a big camp thinking that there is, but it's highly debatable. So if I were to like look at that diagram, I could put a big, sorry, going way back, there. For the high pressure ice, you could put like a big question mark there because we don't know if it's there. We don't know how thick it is. It's like really deep down. We know there's no molten core in Titan from some Cassini measurements, but high pressure ice, we have zero idea. But it could be there. And so, especially because it's so cold, but then, yeah. And if it is there, there's different scenarios also that if we have porous high pressure ice and it's really saline, and then it could still, we could still have some enrichment of the ocean. So even if it is there, depending on its composition, there could still be enrichment of the ocean. So it may not necessarily be a barrier to life also, if it is there.
Thank you.
Yeah.
Hi, nice talk. I would like to ask you if you had considered the influence of the tidal dissipation in your models.
Oh, wait, so the tidal dissipation? Do I incorporate that?
If you had considered that influence in the generation of Titan quake, sorry.
Yeah.
So have you considered the influence of the tidal dissipation?
No, we're not considering tidal dissipation in the models. We're assuming just a very perfect Titan. But I also don't think... we're considering attenuation within the ice shell, but tidal dissipation, we're not really thinking about, I think. And because, I don't think we need to.
Yeah, tidal heating on air provoked earthquakes. If you synthesize the seismic analysis and the influence of the tidal dissipation. So on Titan, I don't know how much is a contribution of the tidal. So that's why I am asking you if you have considered this.
We haven't considered
this parameter in your model. But it could be great if you include also to see how much is the contribution of the tidal dissipation for the generation of Titan quakes on your models.
Yeah, I don't know if it has like a huge. So the tidal, I don't think that will have like a large effect, which is why we've left it out. But I think it is worth.
Yeah, also depend of the distance between the Titan and Saturn. So I don't know. That's why I was asking you.
Yeah, thank you so much. Yeah.
Okay, one more question.
So I'm not a planetary geologist, but I do know that one of the limitations for our understanding of the interior of Mars with the InSight mission was that we only had a single seismometer.
Yeah.
In your data, are you modeling basically seismology being measured by a single seismometer? And do you think having multiple seismometers on the surface of Titan would give you further resolution in terms of the thickness of methane clathrate lid?
100%. It would be amazing to have multiple seismometers on Mars, also on Titan. But I think just with experimental mission constraints, like they can only have one.
Have you done any modeling to see if you could get further resolution with multiple seismometers?
So it's not really about like getting the resolution with. So we can generate perfect seismograms. It's just how well we'll be able to see and detect things.
I see.
It's easier to like triangulate events and things with when you have multiple seismometers. But yeah, we can. Essentially, if we could see like deeper events if we have more seismometers, we'd have just greater sensitivity overall. But we unfortunately don't have that.
Yeah.
So we have to do what we can with one.
Thank you, Andrea.
Yeah.